We see it in galaxies colliding, where the atoms collide and make X-rays, and the dark matter traced out through their ability to bend space under Einstein's laws. We can trace out when we see galaxy collisions or clusters of galaxies collisions, we can actually see that the dark matter appears to travel right through. Is there any way for us to detect dark matter here on Earth? That is a quest that people have been trying in mines, underground mines, looking for example, the very occasional interaction between dark matter and normal matter. Now, many theories of dark matter predict that this will occur. It's just very, very rare. And so we have been building progressively larger vats of cooled xenon, liquid xenon, looking for these interactions. And at this point, there is no discovery, despite a huge amount of effort being able to look. We're going to be able to continue these experiments into the years ahead, but at some point we will be overwhelmed by, for example, neutrinos, which will go through and start to overwhelm any ability to make measurements. But of course, we don't really know what dark matter is, so we continue to look for clues other ways. Maybe we could create it in CERN, in the Large Hadron Collider, or in a similar set of experiments. Or maybe we will see some unexpected evidence of it in space. For example, it occasionally interacting with itself and creating gamma rays that we can detect here on Earth. At this point, we've seen occasionally maybe some things to get excited about, but no real evidence that points us in the right direction. Of course, we could be incredibly unlucky. Maybe dark matter doesn't interact with anything except for via gravity, in which case astronomy will continue to be the only way we can get a handle on its existence. But maybe theory will give us an insight that way as well. It could go through and naturally arise from future theory of particle physics not yet created. Dark energy is even harder. Dark energy is everywhere, as near as we can tell, and keeps on, no matter how we look at it, replicating the most simple theory of it from Einstein. The way we know how to look for dark energy right now is seeing whether or not it gets created exactly as space is created in the expanding universe, or whether or not it's created a little slower or a little faster than that bit where it's tied directly to space. The only way we know how to test that is by doing increasingly more sophisticated and detailed experiments of the universe and how it expands over time. So at this point, we have literally looked at thousands of supernovae compared to the dozens that we did in 1998. And as near as we can tell, the universe continues to accelerate as if it was made of the cosmological constant at about 70%. Very accurate measurements have been made using galaxy surveys. We talked about galaxy surveys being a way to look at the phone. But the galaxy surveys actually capture the sound waves of the Big Bang that we see in the cosmic microwave background. And those sound waves are seen in the foam structures of galaxies throughout the universe. And because there's literally billions of galaxies out there to measure, you can track over time those sound waves. And we have done that with increasingly and increasing accuracy. To this date, once again, what we see is the cosmic microwave background to the present. We see a universe whose sound waves are essentially propagating as we would expect in a universe full of a cosmological constant. So in the future, we can expect new experiments. We have dedicated telescopes in space. The Nancy Roman telescope, the Euclid experiment, that are going to go through and try to trace with even better accuracy the cosmic expansion over time. I'm not sure what they will find, but we won't know unless we look. But maybe something will come from an unexpected source. For example, some of the new telescopes that we have
James Webb begins a voyage back to the birth of the universe.
The James Webb Space Telescope to be launched in 2021, in the very near future. Or the giant telescopes being built on Earth, like the Giant Magellan Telescope or the Extremely Large Telescope. These telescopes will allow us to look back in time like never before to the first stars. Now, at this point, it may not be the best way to probe dark energy, but maybe it will allow us to create an experiment not yet thought about that gives us a pointer towards dark matter or dark energy. I don't know. What I do know is that astronomy continues to thrive when we're able to look further and farther than ever before. And so these experiments hopefully will give us a glimpse into new ways of thinking about the world. Another exciting way to look into the past is the new observatories that are able to see gravitational waves for the first time. Being able to use gravitational waves allows us to look back to black holes merging in the very early universe. We know that with current telescopes that black holes formed very soon after the Big Bang, maybe as soon as, a couple 100 million years for sure. But we already had supermassive black holes, ones that are 1 billion times the mass of our sun, in place 1 billion years after the Big Bang. How we got those, we're not sure. And these new generations of telescopes will allow us to look back. The gravitational wave detectors actually seeing the merger of black holes and telling us when these turned on and how many over time. Maybe this will give us an idea of how the universe came together in its earliest days. Maybe there's a whole class of exploding stars that we don't know. Maybe the whole set of exploding stars to begin with that we think exist didn't really exist. That the first very large stars collapsed and formed black holes directly. Or maybe the universe was born with black holes that we didn't know about. We need to go out and look to know and understand. One of the things that I worry about is that Einstein's theory of general relativity remains decoupled from particle physics. So the physics of CERN and the physics of astronomy and cosmology remains unresolved. How do we bring together into a theory of everything gravity and quantum mechanics? I keep hoping that the solution to dark matter and dark energy might emerge from solving that problem. But we won't know until we do it. If we go through and we think now around other types of measurements where we can go even earlier, we have radio telescopes in the form of the Square Kilometer Array that will be able to look back even before stars existed, because they are sensitive to hydrogen, cold hydrogen, left over from the Big Bang itself. And as hydrogen goes through and has essentially its atomic structure flip from one way to another, it emits a radio wave very similar to the frequency that we use for our phones here on Earth. That allows us to get a picture of the universe before the first stars. And that technology is coming over the coming decades in giant observatories being built here in Australia and in South Africa. So what comes with the universe in the future? We can look back at the past, but what can we expect for the universe's future? Well, the future of the universe is ultimately a battle for domination between gravity that pushes and gravity that pulls, dark energy and dark matter. And what we know is already dark energy is 70% of the universe. Dark energy has won the battle of the universe. And as the universe expands, dark matter becomes less and less dense. You have the same amount of dark matter as the universe gets bigger and bigger. Dark energy is part of the universe, the fabric of space itself. As the universe gets bigger and bigger, it stays constant. And so it becomes more and more dominant over time. The bigger the universe gets, the more dark energy is able to push on it. And so the universe's expansion gets faster and faster over time. The acceleration we've been seeing in the past will continue and become faster and faster over time. So fast that galaxies we see today will in the future be accelerated beyond our ability to see them. The light, as it tries to travel through the universe, will not be able to reach us. The light will get stranded in the expansion of space and lost forever. So we are literally living in a special time when we can see more universe than what we will be able to see in the future. The future of the universe is dark energy. Now, I say that statement with authority, but I should be cautious because we do not exactly understand everything about the universe. And so if dark energy were to change in the future and become more or less dense than being constant, perhaps the trajectory will change. Perhaps there's something else in the universe we haven't thought about. Unfortunately, you can only extrapolate into the future, predict the future, if you are omniscient. Indeed, there are certain forms of dark energy where dark energy becomes a little stronger over time, a little more dense. The more the universe expands, the density of dark energy increases. This type of dark energy actually causes the universe to accelerate faster and faster, not just such that galaxies disappear, but every part of the universe will disappear to the subatomic level. We would live in a universe in the future where one day the stars would start going out, the sun would suddenly disappear, and then not too much longer later, we would suddenly find our own atoms spread so far apart that light would not be able to travel. That's known as the Big Rip. Now, I don't think that's what's going to happen to the universe, but I can't rule it out. And that's one of the reasons why we keep measuring. Whatever happens for the universe, we know that as long as the universe keeps on expanding at an accelerating rate, that the universe will continue to expand faster and faster, and what we can see will become less and less, slowly fading over time. We will find ourselves in the future a universe that is dark, without information. And so now is the time to explore the universe. So the universe ends not in a bang, but apparently in a whimper. It is a universe that is rich with literally trillions upon trillions of galaxies, and yet it is finite. We can never know everything about the universe, but the universe is so big, I think we have lifetime upon lifetime to keep exploring it. Thank you very much for joining me in this Great Minds series.